In this video, we're going to continue solving equations. Now we're going to look at higher degree polynomial equations, equations with rational exponents, and equations which are quadratic in form. By a higher degree polynomial, I mean a polynomial of degree 3 or more. And in general, when I'm solving any equations, if I feel stuck, I get 0 on one side. And with polynomial equations of degree 3 or higher, this is generally the best strategy. There are some simple examples where maybe that's not going to be best, but for most higher degree polynomial equations, you're going to want to get 0 on one side. So in the example you see on the screen, x cubed minus 12 equals 4x minus 3x squared. There's no obvious strategy for what to do if I leave it like this. So I'm going to move everything to one side. I'm going to get 0 on one side. So I'm going to subtract 4x and I'm going to add 3x squared. And when I write those steps on the left side, I'm going to write them in the opposite order because I like to have my terms in descending order from highest power of x to lowest power of x. So the result of that step is x cubed plus 3x squared minus 4x minus 12 equals 0. And that gives us a 4-term polynomial on the left side. If I want to get that factored, I might try factor by grouping. So I'm going to group the first two terms and I'm going to group the last two terms. The GCF of the first two terms is x squared, leaving behind x plus 3. In the back, you want to make sure you pull out a negative 4 so that you get another copy of x plus 3. If you factor by grouping in a 4-term polynomial and these two sets of parentheses don't match, then factor by grouping has failed. But because these match, I can pull that out. X plus 3 is the GCF of this new expression. So I can pull an x plus 3 from both terms. When I pull x plus 3 from the first term, it leaves behind x squared. And when I pull x plus 3 from the back term, it leaves behind a minus 4. And that's a difference of squares. I can break that down even further. That's x plus 2x minus 2. And we've seen enough applications of the zero factor theorem to skip the step of writing the equations here. The solutions here are easy. What would make the first set of parentheses equal to 0? Well, negative 3. And of course, if that was equal to 0, then the entire product would be equal to 0. That's the zero factor theorem. The second set of parentheses would be equal to 0 when x is negative 2. And the last set of parentheses would be equal to 0 when x equals 2. Because this was a polynomial equation and we didn't do any weird steps like squaring both sides or clearing out denominators, we didn't run the risk of generating any extraneous solutions. So as long as we didn't make any silly mistakes, these solutions are okay. We know they're all going to work. You should always check your answers, don't get me wrong, but there's nothing about the steps that we use that requires that we check our solutions. We didn't generate any extraneous solutions here. So all three of those are solutions. Let's look at another example. This is a 5th degree equation, what we call a quintic equation. And there's a step here that might be calling out to you, but you need to be careful. A lot of people will start an equation like this by dividing everything by x cubed. That actually eliminates one of the potential solutions, so you don't want to do that. Instead, let's follow our process and get 0 on one side. I would actually do that by subtracting these two terms over to the left side. That makes sure that my leading coefficient is positive. That always makes me more comfortable. So the result of that step is x to the 5th minus 6x to the 4th plus 9x cubed equals 0. Comparing with 0 is always a good idea because then we can apply the zero factor theorem if we can get the polynomial in a factored form. Here we need to start by pulling out the GCF. Rather than dividing by x cubed, we're just going to factor it out. That way that factor can still yield a solution. The expression in the parentheses when we factor out x cubed would be x squared. X cubed times x squared would give us x to the 5th minus 6x. X cubed times negative 6x would give us negative 6x to the 4th plus 9. And that's still equal to 0. Now we have this quadratic polynomial and we can factor that by guess and check. X times x is the only reasonable way to get x squared. To get 9 in the back, we could take 9 times 1 or 3 times 3. Well, 3 plus 3 is 6, so that seems like the better guess. And then to make them multiply to a positive but add to a negative, I need them both to be negative. So it's 2 copies of x minus 3. I know I just skipped this step in the last problem, but we haven't seen one with a cubic term out here, so I'm going to write this out. There are two possibilities, either x cubed equals 0 or x minus 3 equals 0. I know there are 2 copies of x minus 3, but there's no good reason to write it again because it's going to yield the same solution. If x cubed equals 0, then x equals 0, and that's the solution we would have lost if we divided everything by x cubed. That factor would have disappeared, and we wouldn't have gotten the solution x equals 0, which is obviously a solution because if I plug 0 in for x in all three terms, you get 0 equals 0. The less obvious solution is x equals 3, but it's easy to see now that we have it factored. A fifth degree equation can have as many as 5 distinct solutions. This one only has 2 because of the repeated factors. We've got 3 copies of x and 2 copies of x minus 3. So just 2 solutions here. Again, nothing we did would generate extraneous solutions, so we don't have to worry about that here. So with these higher degree polynomial equations, you want to get 0 on one side and try factoring. I think we're ready to move on to examples with rational exponents. A rational exponent is just a fractional exponent. So I have an example on the screen here. X to the 2/5 equals 4. I have the step I would use written out at the top here, but I want to explain the logic to it. When you solve for x, you're trying to eliminate the coefficient, make it a 1, which we already have here, and you're trying to make the exponent a 1 as well. When you've solved for x, you have x to the first equals some number. Well, what algebra step could I do to this in order to turn the exponent into a 1? Well, when you raise a power to a power, you multiply the powers. So if we could think of something to multiply 2/5 by to turn it into a 1, then that would be a useful step. Well, we know that you multiply a fraction by its reciprocal in order to get 1, and that's what the step says to do. If you have an equation of the form x to the m over n equals a, where a is just a number, try raising both sides to the n over m power. That is, use the reciprocal. Now, I note here that if you're not careful, you'll miss a solution. You have to remember what your step means. I'm going to explain that as I go. I have an otherwise here, but we'll get to that in the next example. So my step would be to raise both sides to the 5 over 2 power. The idea is simple on the left side. If you raise a power to a power, you get to multiply the exponents. And when you take 2/5 times its reciprocal, 5/2, you get x to the first, which is just x. That's what we were trying to achieve. You just have to realize what we were doing on the right side, and here's where we might have to go back and throw something in, because we're going to miss a solution if we're not careful. When your denominator is 2, you're really considering the square roots of this number, and we know that positive 4 has 2 square roots. So technically, when I do this 5 over 2, I have to put in a plus or minus. Now that's very easy to miss, so I'm going to show you an alternative way to think about this so that you don't miss that step. But if you do it my way, you have to remember to put in that plus or minus. After that, though, this is easy. You just have to remember what this tells you to do. The denominator is a square root, so that's 2. And then we raise that to the 5th power, that's 32. Maybe I should write that step out. So the arithmetic there was 4 to the 5/2 means the square root of 4 to the 5th. And the principal square root of 4 is 2, so this is 2 to the 5th, which is 32. The plus or minus came from the fact that we have to consider all possible square roots. Now again, that's easy to miss, so I say down here that you might just try raising both sides to the n power first. N was the denominator in my expression, so you might start by raising both sides to the 5th power. This makes the number on the other side bigger at first, but in the age of calculators, that's not an issue. So let me rewrite the problem. X to the 2/5 equals 4. And I'm going to start by raising both sides just to the 5th power. The idea here is that 2/5 times 5 is just 2, and we won't have to deal with the fractional exponent anymore. We'll wind up with a polynomial equation. 4 to the 5th is 1024. And now you see that we've got x squared equals 1024, and when we use extraction of roots, we need to consider both square roots. I don't usually write this step in, but let me do it here just to emphasize my point. We need to consider all square roots of 1024, both the positive and the negative. And using a calculator, you can come up with the square root, which is 32. Same answer. We can go back and check our answer here. It's not necessary because we raised both sides to an odd power, to the 5th power. If that number was even, then we run the risk of generating an extraneous solution, and we have to go back and check. So that's what you do when you have a variable raised to a fractional exponent, and that's set equal to a number. But what do you do when you have another variable term floating around? In this example, we have x to the 5/4 equals 9x. Raising both sides to the 4/5 power here is not a good idea. Let me show you. If I were to raise the left side to the 4/5 power, that is going to give me x, but unfortunately on the right side when I raise to the 4/5 power, I don't get to pick and choose what gets raised to the 4/5 power, and now the x is going to have a fractional exponent on it. So then you're going to raise both sides to the 5/4 power, and then you're going to raise both sides to the 4/5 power and go back and forth. You'll be stuck in an infinite loop for the rest of your life. That won't work. The other option of raising both sides to the 4th power, like we did in the second go through of that example, that's not a bad idea, but I'm going to suggest an alternative, which is to get 0 on one side. I'm going to subtract 9x. This step is more flexible and will work when you have more than 2 terms. Now we're going to try factoring just like we did before. And again, don't be intimidated by factoring with fractional exponents. You find the smaller of the 2 exponents. 1 is smaller than 5/4, so I'm going to factor out an x. And then to figure out what's left over when I factor here, I just subtract. I take the exponent that I'm starting with, 5/4, and I subtract away the exponent that I'm pulling out. I'm pulling out an implied 1. 5/4 minus 4/4 is 1/4, and so this leaves behind an x to the 1/4. Notice that if I were to distribute, I would add the exponents, and 1 plus 1/4 would be 5/4. In the back, I'm pulling away the x. I'm just left with a 9. That's equal to 0. So we get 2 cases, either x equals 0 or x to the 1/4 minus 9 equals 0. This one's done. There's no easier equation than x equals 0. Over here, I add 9 to both sides, and I get x to the 1/4 equals 9. And now we're back in that situation we were talking about on the previous slide. I'm going to raise both sides to the reciprocal power. I'm going to raise both sides to the 4th power. Now that's an even power, so we have to be careful here and make sure we don't generate an extraneous solution. 9 to the 4th is 6,561. So now we should check to make sure that that answer is right. The left side of our equation was x to the 5/4, so I'm going to take 6,561 and raise it to the 5/4 power. To get an exponent in this calculator, I use the little caret key. If you have a newer calculator, you'll actually get a superscript and you can just type 5 divided by 4. For those of us with the older operating system, you're going to want to use parentheses and do 5 divided by 4 to make sure that that entire fraction is used as the exponent. That comes out to 59,049. The other side of our equation was 9 times x, so that's 9 times our proposed solution of 6,561. Also comes out to 59,049. I felt compelled to check because we raised both sides to an even power. If you have experience with this, you might have recognized this wasn't going to be extraneous because the right side was a positive number. If we had raised a negative number to an even power, that's where you run the risk of generating an extraneous solution. So if you can see that, you don't actually have to run the check, but you at least need to consider it. Both of these are solutions. So again, if you have multiple variable terms, get all the variable terms to one side, try factoring so you can apply the zero factor theorem. If you have an expression with a fractional exponent set equal to a number, raise both sides to the reciprocal power and then be careful. Sometimes you have to consider cases, like we did here when the denominator was an even number. Sometimes you have to worry about extraneous solution. The last topic I want to cover in this video is equations which are quadratic in form. And the first one's just going to be a polynomial equation. It says x to the 4th minus 5x squared plus 4 equals 0. This is a polynomial equation of a higher degree, so we want 0 on one side. That's already done. But now we have to get this thing factored. And some of you might have enough factoring experience to know how to factor this, but for a lot of people, the higher exponents makes this more difficult. And so I'm going to suggest a step to try if you can't get this factored as it's written. If you can factor this as it's written, then the steps I'm suggesting are unnecessary. But if you're not sure, if you need some sort of boost or help, then consider the following. First, what do I mean by an equation that's quadratic in form? If the equation you're working with can be written in the form ax to the 2k plus bx to the k plus c equals 0, we say that it is quadratic in form. Well, that clears everything up, right? Nothing makes things clearer than a bunch of math symbols. Let me explain. Here's basically what this says. If you rewrite your equation so that you have 0 on one side, and you notice that one of the exponents on the variable is 2 times the other exponent, and then the third term is a constant, we say an equation like that is quadratic in form. That's exactly what we have in our first example. The first exponent is 2 times the second exponent, and the last term is a constant. Now, what's the point behind bringing that up? you want to try to factor that expression on the left, and that can be difficult because of the higher exponent. And here's the substitution you should consider. You should let u replace the x to the k, expression with the exponent that has the smaller magnitude. That substitution will make everything look easier to factor. You can do the factoring, and then you can put everything back the way it was. Let me show you what I mean. So in this example, we have x to the fourth minus 5x squared plus 4 equals 0. And again, some of you might be able to factor that as it's written. That's awesome. If you're having trouble with that because of the higher exponents, that's completely normal. And so we're going to try a substitution. We're going to let u replace the x squared, the smaller in magnitude. I'm saying it that way because sometimes the exponents are negative. I'll give you an example of that. Now, that gives us a second substitution for free. As a consequence, if I square both sides of that statement, I get u squared on the left. On the right, I get x squared squared, but that's x to the fourth, which is the first term. Notice that's not a choice that I'm making. That's a consequence of my first substitution. Now, why would I do that? Well, it's going to make the equation easier to work with. Let me keep running with the substitution here. X to the fourth can be replaced by u squared. Minus 5x squared, well, I can't replace the minus 5, but the x squared gets replaced with u. The constant term didn't have a variable, so there's nothing to substitute there. And now we have a quadratic equation. And this is why we say it's quadratic in form. It's not literally quadratic. We call this quartic because of the fourth power. But we can rewrite it as a quadratic just to make us more comfortable in factoring. We should all be able to factor this. This is u minus 4 times u minus 1. And now you have a choice what to do. I like to solve these equations first and then back substitute. Some people like to substitute right away. So I would solve these. We've done this enough. I'm just going to jump to the solutions. U equals 4 and u equals 1 are the solution in terms of u. But remember, we weren't solving for u, we were solving for x. So now we back substitute. I know that u is equal to x squared, so this is x squared equals 4. And I know that u is equal to x squared here as well, so this is x squared equals 1. A common question I get is, what happened to the x to the fourth? That was the substitution for u squared. I don't have a u squared down here, so I don't back sub for that. I have u equals 4, that becomes x squared equals 4, and I have u equals 1, that becomes x squared equals 1. And now we can use extraction of roots. Remember to consider both cases because this is an even root. The two square roots of positive 4 are plus or minus 2. The two square roots of positive 1 are plus or minus 1. And we get 4 solutions. And they all work. We didn't do anything here that would generate an extraneous solution. This is just a polynomial equation. So all 4 of these work. Now, if you can look at the original polynomial and see that it factors to x squared minus 4, x squared minus 1, and you want to continue with that step, that's what you should do. I'm not saying that you have to use the substitution. The substitution is just a nice crutch that you can use in order to help you get the factoring started. Here you might have been comfortable because this is a polynomial, but there are other scenarios we have to worry about. Like, what about fractional exponents? Again, this can be factored without doing a substitution. But for most of us, it's a little bit intimidating to try to factor with fractional exponents. So let's see if this meets our condition. All right, we already have 0 on one side. That's beautiful. Is the first exponent 2 times the second exponent? Well, let's see. 1/6 times 2 would be 1/6 times 2 over 1. That's 2/6, which is 1/3. Yeah. The first exponent is 2 times the second exponent, and the last term is a constant. That's what it means to be quadratic in form. This means that our substitution will work. And you always let u replace the exponent that is smaller in magnitude. So the x to the 1/6. The reason you do that is when you square both sides of that replacement, when you raise a power to a power, you multiply the powers, and you know that's going to give you the higher exponent because you already verified that the first exponent is 2 times the second exponent. If this didn't pan out, then the substitution isn't going to work. You need to try something else. Now we can rewrite this. Instead of 2x to the 1/3, we can write 2u squared. U squared is the replacement for x to the 1/3. Instead of minus 3x to the 1/6, we can write minus 3u, because u is the replacement for x to the 1/6. There's nothing to replace in the constant term, and now we have a quadratic equation. We should be more comfortable with this. Even if you can't get this factored, now you have the quadratic formula to use. This factors. This is 2u minus 1 times u minus 1. Again, I like to solve these before I make the back substitution. So I know that 2u minus 1 equals 0, or u minus 1 equals 0, and I'm writing them out here because this equation takes a little bit of work. This is u equals 1/2 because I'm going to add 1 and divide by 2. This is u equals 1. But those aren't our solutions. Remember, you have to back substitute. What was u equal to? It was equal to x to the 1/6. So x to the 1/6 equals 1/2, or x to the 1/6 equals 1. How do we handle a rational exponent like that? We raise both sides to the 6th power, the reciprocal power. The one on the right is the easy one. 1 to any power is 1. So one solution is x equals 1. And because 1 to any power is 1, you can see that that works. 2 times 1 is 2. 3 times 1 is 3. 2 minus 3 is -1. -1 plus 1 is 0. On the right, we get 1/64. And because we raise both sides to an even power, we should check for an extraneous solution. I'm going to spare you watching me type this into the calculator, but I promise you that this one works as well. You need to check it because we raise both sides to an even power, but this one works. So we get 2 solutions. One more. We covered a regular polynomial example. We've covered a fractional example. Let's do one with negative exponents. And these ones with negative exponents are the reason I keep saying the exponent with the smaller magnitude when we're making our substitution. So the equation here is x to the -2 minus 2x to the -1 minus 35 equals 0. There is an alternative to using a substitution here. You could multiply everything by x squared, and that would be allowed. If this was an exam question, you would be allowed to solve it by an alternative method. You wouldn't have to use a substitution. But of course, I'm trying to demonstrate this method here, so that's how I'm going to do it. I noticed that the first exponent is 2 times the second exponent. I don't think I need to show that arithmetic. 2 times -1 is definitely -2. And the last term is a constant. Exactly what we need for the substitution to work. Now, -2 is smaller than -1, but I'm going to let you replace the expression with the exponent that has the smaller magnitude. And that's because when I square both sides, I need to get that first term. So that's why I'm being careful about how I say it. It's not correct to say you let u replace the expression with the smaller exponent. You have to include that you're taking the exponent with the smaller magnitude so that when the squaring step gets done, you wind up generating that other term. So let's make our replacement here. X to the -2 gets replaced with u squared. Minus 2x to the -1 gets replaced with minus 2u. The minus 35 doesn't get replaced at all. And we set that equal to 0. See if you can get this factored. This factors to u minus 7, u plus 5. And so we get 2 solutions for u. We get u equals 7 or u equals -5. And those are our answers, right? Nope, 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 nope. Those are not our answers. We have solved for this u that we just made up, but the equation is asking us to solve for x. We want to know the values of x. Now we have to back substitute. I know that u is equal to x to the -1, so I get x to the -1 equals 7, or x to the -1 equals -5. And let me show you how to solve these equations. We'll transfer this to another slide. Okay, so how do you solve an equation like this? Well, there are actually a few different ways you can think about it. One way to do this is to translate x to the -1 into what it means. It means 1 over x. So 1 over x equals 7. And then you can use logic here and say, well, if 1 over x is equal to 7, then x must be the reciprocal of 7. So that's x equals 1 over 7. An alternative to that would be to multiply both sides by the denominator. Get 1 equals 7x, and then divide both sides by 7, and get x equals 1 over 7 that way. That's a second option. Or a slick way to do this is to not consider it as 1 over x, and instead just raise both sides to the -1 power. Why would that work? Well, when you raise a power to a power, you multiply the exponents, and -1 times -1 is +1. It's the same idea that we were using before. We're multiplying by the reciprocal of -1. It just happens to be that the reciprocal of -1 is itself. The right side is 7 to the -1, which means 1 over 7. So any of those three methods would work. As you might guess, I'm partial to that last one, so that's what I'm going to do here as well. I raise both sides to the -1. The reciprocal of -5 is 1 over negative 5, but I write that as negative 1/5. And those are our two solutions. The only thing we'd have to worry about here is if we got an answer of 0. You can't raise 0 to a negative exponent because that would be division by 0. Nothing else we did here would generate extraneous solutions. So as long as we didn't do anything silly, both of these should work. So there's three examples of equations that are quadratic in form. A polynomial example is an example with fractional exponents and an example with negative exponents. You don't have to do the substitutions. Sometimes you might be able to factor it without making the substitution. Do that. Sometimes there might be an alternative step, like in this example where we could have multiplied everything by x squared. That's fine. If that's what you'd rather do, do it. But when you feel stuck, like in an example like this is the one where I'd expect most people to need the substitution. Consider it. First, verify that you've got an equation that's quadratic in form. The first exponent is 2 times the second exponent, and the last term is a constant term. And then make the substitution. You let u replace the expression whose exponent has the smaller magnitude. That guarantees that u squared will replace the other exponential expression. You'll wind up with a quadratic that you can either factor or use the quadratic formula on. Then make sure you back substitute because you want to solve for the original variable, not for this u that you made up. When you back sub, you might need to do a step or two to actually solve for your variable, and then if necessary, check those solutions. Make sure you do some practice problems. If there's anything that I can clear up, send me an email. See me in an office hour.